So what on earth are flux integrals? Well, flux integrals, if we have a fluid with a continuous velocity vector field, right? So fluid is possibly in motion, and an imaginary surface S is submerged in the fluid. Again, the fluid could be a gas. Then the volume of fluid crossing the surface S per unit of time is called the flux of F across S. So you got a vector field F representing fluid and a surface submerged in that fluid, and the amount of fluid crossing our surface S per time unit is called the flux of F across S. If we cut the surface S into small itsy-bitsy units in the usual way, we can assume that F is nearly constant across one of those bits of surface. And so the amount of fluid crossing del S per unit of time is approximated by the volume of a column of height F dot n. That would be the vector field, the force field, or whatever we've got, dotted with a normal vector or a unit vector normal to the surface. If you think about that, you'd realize that that's given. So the force field's projection normal to the surface, that's what that says, right? And base del S, that's, base is the piece of the surface we're looking across. So the amount of fluid crossing that portion is del V, that's the amount crossing that during that time unit, is F dot n times del S. That's times the size of the itsy-bitsy piece of surface it's crossing. So column height times size, if that makes sense, times size of the thing that's column of fluid above. So add all these up for the surface S to get the amount of fluid for the entire surface, and that is called the flux integral. So here's our vector force field, if you want. Mn and P have continuous first partial derivatives on a surface S oriented by a unit normal vector n. Then the flux integral of F across S is given by the sum of F dot n ds. Think about the ds being when these approach 0, that turns into a ds, and you can see that it's that. S would be some double integral representing the surface. So if the fluid is not uniformly dense, that would complicate things. And P of xyz is the density of the fluid at the point xyz. Sorry, I said P, that should be rho of xyz is the density of the fluid at xyz. Then the integral, same integral as this, only with a multiplier of rho of xyz also as one of the factors. So that represents the total mass of the fluid crossing the surface S per time unit. So how do we evaluate such a flux integral? That S is an oriented surface given by z equals g of xy, and R the projection of S, the shadow if you want, on the xy plane. And the flux integral's orientation, the flux integrals are, and that's with oriented upwards and downwards respectively, each one given here. F dot n ds, which is double integral over region R, which is the shadow on the xy plane, of F dot negative g sub xi minus g sub yj plus k dA, or if it's oriented downwards, this, and you could probably guess what the difference between those two would be. But let's set up one. Let's set up the integral to find the flux of F through the surface S, where n is the upper unit normal vector, to S where F equals xi plus yj, and S is the plane 2x plus 3y plus z equals 6 in the first octant. So there's our surface, a plane in the first octant, and here's our force field F, and we'd like to know what's the flow across S in our first octant. So if we solve that for z, that's an obvious one there, and partial with respect to x is -2, partial with respect to y is -3, so f dot n is xi plus yj, that's the f, dot n, which is 2i plus 3j plus k. That comes from well, you could look at it as either one of these, right? I guess it must be this one. So yes, it's this one I'm using with oriented upward, because the negative of -2. So that's it. And that comes out to be 2x plus 3y. Now we need to find the limits of integration and an order of integration, so we need to find the region R in the xy plane. Well, z equals 0. We've got 2x plus 3y equals 6, or y equals -2/3 x plus 2. And you can see in the picture below why we have such a region here. See, upper is -2/3 x plus 2, and lower, of course, is the x-axis, and then y goes from 0 to 3. Oops, you know what? I've got my axis backwards here. No, I'm sorry. It was y that goes from 0 to -2/3 x plus 2. It's x that goes from 0 to 3, so my axes are just fine the way they are. Okay. Wowzers. So then this is a fairly easy to operate integral. I just said to set it up, we didn't have to evaluate it, but that's easy to evaluate. But what do you think would happen if we use the lower unit normal vector to orient S, and what does that say about the actual result regarding mean of flux? Well, I think you see it would just be negative. And if fluid's flowing across the vector one way above the surface, below the surface, it should be doing the opposite. So suppose the oriented surface is given by the vector valued function R of uv. We'll tell you what, we'll look into that with the next video.